All right, so buckle up because today we're taking a deep dive into a hypothesis. So out there, it might just rewrite the very laws of physics as we know them. We're talking about the hypothesis of unified gravity, or as it's more playfully known, hug.
And the name really does say it all, because this isn't just some minor tweak. It throws out almost everything we think we know about gravity, how it works, what it even is.
The best part, this whole thing started because a science fiction author needed a way to power his spaceships between the stars. Like you'd think he'd just say warp drive and call it a day, but no, this guy went all in on the physics.
Yeah, Gerald Welch, the author in question, he wasn't content with just making stuff up. He wanted something that at least sounded plausible. And that's how he ended up questioning one of the most fundamental forces in the universe.
Okay, so what is it about gravity that would send someone down a rabbit hole like that? We all experience it every day.
You'd think it'd be simple, right? But it's actually one of the biggest mysteries in physics. See, we've got these four fundamental forces that govern everything in the universe. You've got the strong force holding atomic nuclei together, the weak force responsible for radioactive decay, electromagnetism, which covers all things electricity and magnetism.
And last but not least, gravity.
Exactly. The one we're most familiar with. But here's the thing. Out of all of them, gravity is by far the weakest. And it's the only one that only attracts. Think about it. All the other forces have a push and a pull, some kind of balance going on. And Welch just couldn't wrap his head around why gravity would be any different.
So he went looking for some kind of anti-gravity, something that would push things apart instead of pulling them together.
You got it. And his first thought was this concept of negative mass. Basically, the idea that some exotic type of matter could exist with the opposite gravitational effect.
So instead of pulling things in, it would push them away.
Exactly. But even Welch wasn't completely sold on that idea.
So what changed his mind? What was the light bulb moment?
It all clicked when he started thinking about vacuum energy. Now stick with me here because it sounds kind of out there. Vacuum energy is this inherent energy that exists even in completely empty space. And it turns out this energy has a naturally repulsive effect.
Wait, so you're telling me empty space itself is trying to push things apart?
That's the gist of it. It's like this constant subtle outward pressure. And that was Welch's big aha moment.
Yeah.
What if instead of needing some invisible negative mass, the repelling force was coming from empty space itself?
Okay, now that is wild. So how does that lead to a whole new theory of gravity?
That's the core of Hug. It proposes that the universe's natural state isn't stasis, it's expansion. This outward push driven by vacuum energy, what Welch calls inverse gravity, that's the default setting. And the gravity we experience in our daily lives, the attraction described by Einstein, that's more like a localized phenomenon. Imagine it like dense in a giant expanding sheet.
So it's like the universe has this default setting of pushing outward, and then you've got these pockets of matter like galaxies where normal gravity creates these concentrated areas of attraction pulling things in.
A fantastic way to visualize it. Hug isn't saying Einstein was wrong. It's more like his theory of gravity is just one chapter in a much longer book.
Yeah. Okay, I think I'm starting to wrap my head around this whole inverse gravity thing, but like how does this fit with what we actually observe out there in the universe?
That's the million-dollar question, right?
Yeah.
Like, does this actually explain anything, or is it just a cool idea?
Exactly. I mean, we know the universe isn't just expanding, it's expanding faster and faster all the time, like it's hitting the gas. And that's where things like dark energy come into play, right? Trying to explain that acceleration.
And that's where Hug gets really interesting. See, in the standard model of cosmology, you need this mysterious force called dark energy to account for that acceleration.
Right.
But Hug comes along and says, well, maybe we've got things backwards.
Backwards how?
What if this outward push isn't some extra force like dark energy, but rather it's just a fundamental property of the universe itself, like it's already baked in from the get-go?
So instead of needing dark energy to make the universe expand faster, Hug is saying it's already going full speed ahead because of inverse gravity.
You've got it. And the really neat thing is that this idea actually helps to explain some of the large-scale structures we see in the universe that are incredibly difficult to account for with just the standard model.
Okay, like what? Give me an example.
Well, let's talk about those cosmic voids.
You mean those giant areas of empty space between galaxy clusters?
Exactly. Now, if gravity is constantly pulling things together, how did these voids get so big in the first place?
Yeah, why wouldn't those gaps just fill in with matter over time?
That's the puzzle. But Hug offers a pretty elegant solution. Remember how inverse gravity is stronger in areas with less matter?
Right.
Well, these cosmic voids, they're like the ultimate low-density zones. So in Hug's view, Inverse gravity gets really powerful in these voids, pushing everything further apart and actually making the voids even bigger over time.
So the void itself is almost inflating from the inside out because there's nothing to stop it. That's a pretty wild concept.
It is, and it doesn't stop there.
Oh no, there's more.
Hug also takes aim at another big cosmological mystery, dark matter.
Ah, yes. Dark matter, the invisible stuff that supposedly holds galaxies together.
You got it.
So what's Hugg's take on this cosmic enigma?
One of the main pieces of evidence we have for dark matter is that galaxies rotate faster than they should based on the amount of visible matter they contain.
It's like there's this extra invisible matter providing the extra gravity to hold everything together, right?
Right. But Hug suggests that maybe we don't need dark matter after all. It's just inverse gravity playing tricks on us.
Okay, walk me through this. How does that work?
Since Hug suggests gravity behaves differently depending on the surrounding matter, it predicts that in the outer regions of galaxies where matter is less dense, inverse gravity would have a more noticeable effect.
So instead of needing dark matter to provide the missing gravity, Hug suggests our understanding of gravity itself needs an update.
That's the crux of it. It's a radical shift in perspective for sure, but that's what makes this whole hypothesis so compelling. It really has the potential to turn our understanding of the universe upside down.
This is all incredibly intriguing, but I have to ask, is there any actual evidence to support Hug? Or is it just a beautifully elegant idea? So we've got this really elegant idea, one that could rewrite the textbooks. But how do we actually test it? How do we know if Hug is right or if it's just a really cool story?
Well, the good news is that Hug makes some pretty specific predictions that are different from the standard model of cosmology and predictions that we can actually observe.
Okay, so what are we looking for? What kind of observations would tell us if this whole inverse gravity idea holds water?
Telescopes. We're talking about telescopes here, and luckily we're living in a really exciting time for astronomy. There are some seriously powerful telescopes coming online soon, like Euclid and LSST, and these are going to give us a view of the universe like we've never had before.
Okay, so keep your eyes peeled for news about Euclid and LSST, because they're going to be gathering some crucial data for testing Hug. But what kind of data are we talking about specifically?
One of the key things the telescopes will be studying is something called weak lensing. Imagine light traveling across the universe like it's on a highway. Now imagine that massive objects like galaxies and galaxy clusters create little gravitational speed bumps along that highway.
So these gravitational speed bumps, they're kind of like lenses distorting the light that passes by them.
Exactly. And by carefully measuring how that light is distorted, how its path deviates from what we'd expect if there were no speed bumps, we can map the distribution of matter in the universe.
Okay, I'm with you so far, but how does Hug fit into all of this?
Because Hug proposes a different balance between the inward pull of regular gravity and the outward push of inverse gravity. It actually predicts that we'll observe a subtly different lensing pattern, one that's different from what the standard model predicts.
So we're talking about tiny discrepancies in how light is bent around these massive objects. How could we even measure something that subtle?
That's where these next-generation telescopes like Euclid and LSST come in. They're designed to measure weak lensing with incredible precision. It's like having a cosmic magnifying glass that can see the fine print of gravity itself.
That's incredible. And if those discrepancies match what Hug predicts, that would be a pretty big deal, right?
It would be huge. It would suggest that our understanding of gravity is incomplete, that this force we experience every day is just one part of a much grander cosmic dance. But that's not the only test Hug has to pass.
There's more.
Oh, yeah. Remember those cosmic voids? How Hug explains their formation?
Those giant expanding pockets of emptiness. Of course.
Well, Hug also makes specific predictions about how those voids should be distributed and how they should evolve over time. The standard model, with its reliance on dark matter and dark energy, paints a certain picture of those voids, but Hug offers a completely different perspective.
And by studying the size, shape, and distribution of these voids, we can get another clue as to which model better reflects reality.
Exactly. We're talking about comparing observations with highly detailed theoretical models. It's a meticulous process, but one that could potentially revolutionize our understanding of the universe. And the most exciting part, we don't have to wait decades for these answers. We're going to be getting this data in the next few years.
So we're basically on the edge of our seats waiting for the universe to spill the tea. And you know what's really mind-blowing about all of this? Even if just a fraction of what Hudgy proposes turns out to be true, it makes you realize how much we still have to learn about the fundamental forces driving the cosmos. It's like there's a whole other side to the universe we haven't even begun to explore, and who knows, maybe there's another science fiction author out there right now sketching out a theory that will turn physics on its head. That's it for our deep dive this time, but keep those questions coming and we'll keep digging for answers.